Hello students, welcome to EPG Pathshala. I am Professor Devendra Mohan from Department of Physics, Guru Jambheshwar University of Science and Technology, Hisar, Haryana. Today we are going to discuss about the module Coupling Schemes Part 2. This is in continuation of Part 1 from the paper Atomic, Molecular and Laser Spectroscopy. You will be able to learn about the various coupling schemes, atoms with two or more equivalent electrons, orders of terms and fine structure levels, vector model for two valence electron atom under the LS coupling scheme, selection rules for multi-electron atoms in LS coupling and JJ coupling, spin-spin coupling as well, vector model for two valence electron atom under JJ coupling scheme, electrons in different orbitals as non-equivalent and electrons in the same orbital, that means equivalent electrons. You will be able to learn about the various coupling schemes, atoms with two or more equivalent electrons, orders of terms and fine structure levels, vector model for two valence electron atom under the LS coupling scheme, selection rules for multi-electron atoms in LS coupling and JJ coupling, spin-spin coupling as well, vector model for two valence electron atom under JJ coupling scheme, electrons in different orbitals as non-equivalent and electrons in the same orbital, that means equivalent electrons. Atoms with two or more equivalent electrons. For two equivalent electrons where the values of n and l are same, the values of at least one of the remaining quantum numbers ml or ms must differ in order to satisfy the Pauli exclusion principle. The terms which were possible for two non-equivalent electrons are now not allowed. Let us now see how to obtain terms from a configuration involving equivalent electrons. Before we do so, we must mention two important facts. A closed subshell such as S2P6D10 always forms a 1s0 term only. The closed subshell consists of maximum number 2l plus 1 of equivalent electrons in antiparallel pairs. So that sigma ml is equal to 0, sigma ms is equal to 0, and this means that ml is equal to 0, ms is equal to 0, and so L is equal to 0 is the S state. S is equal to 0, 2s plus 1 is equal to 1, which is a singlet state, and J is equal to 0. That is, the only possible term is 1s0. Hence we conclude that when a subshell is completely filled, the only allowed state is 1, in which the total spin angular momentum, total orbital angular momentum and total angular momentum are all 0. This means that the subshell has no net magnetic dipole moment. The terms of a configuration NLQ are the same as the terms of the configuration NLR minus Q, where Q is the maximum number of electrons, that is 2l plus 1. For example, the terms of P5 are the same as those of P1, the terms of P4 are the same as those of P2, the terms of D8 are the same as those of D2, and so on. This simplification is based on the fact that a completed subshell like P6 gives only a 1s0 term, that means 0 angular momentum. This means that the vector addition of the angular momenta of the terms of P2 to the corresponding quantities for P4 must give 0. From this, it follows that the quantum numbers S and L must be same for P2 and P4. That is, the terms of P2 are the same as those of P4. Calculate the spectral terms arising from two equivalent p electrons written as P2. Let us imagine the atom to be placed in a very strong magnetic field where all the internal coupling are broken down. The individual L and S vectors then precess independently around the magnetic field with quantized components ML H cross and MS H cross respectively, H cross being H by 2 pi. The value of L for a p electron is 1, and hence the values of Ml are 1, 0, minus 1, while those of Ms are plus 1 by 2 and minus 1 by 2. Now all the possible combinations of Ml and Ms for a single p electron are Ml is equal to 1, 0, 0, minus 1, minus 1, 1. Ms is equal to 1 by 2, 1 by 2, 1 by 2, minus 1 by 2, and minus 1 by 2, minus 1 by 2. Thus, there are 6 possible states A, B, C, D, E, F in which a single p electron can exist in an atom, which is described in the table. The possible states for 2 equivalent electrons can be obtained by taking all possible combinations of the above 6 states taken 2 at a time with no 2 alike. There will be 15 such combinations: AB, AC, AD, AE, AF, 5 combinations; BC, BD, BE, BF, 4 combinations; CD, CE, CF, 3 combinations; DE, DF, 2 combinations, and EF, 1 combination. In total of 15 such combinations can be arised. For each of these 15 combinations of very strong field quantum numbers, we add 2 values of Ml to obtain the strong field values of Ml and 2 values of Ms to form Ms, so that sigma Ml is equal to Ml and sigma Ms is equal to Ms. So all these have been described in the table where we have written Ml and Ms values for AB, AC, AD, AE, AF, BC, BD, BE, BF, CD, CE, CF, DE, DF, and EF. So we get different levels. Now coming to the orders of terms and fine structure levels, the relative energies of the various terms and levels which rise from a given electron configuration may be deduced from a set of rules given by Hund. So these rules are: of the terms arising from equivalent electrons, those with largest multiplicity lie lowest, and of the terms with given multiplicity and arising from equivalent electrons, that with largest L value lies lowest. In the multiplets formed from equivalent electrons in a less half-filled subshell, the level with lowest J lies lowest, normal order. In the multiplets formed from equivalent electrons in a more than half-filled subshell, the level with highest J lies lowest, that means the inverted order. Terms arising from half-filled subshell show only very slight fine structure splitting. The lowest terms arising from the half-filled subshells are the S terms and are specially stable. These terms are 2s1 by 2 for half-filled subshells, 4s3 by 2 for a half-filled p subshell, and 6s5 by 2 for a half-filled d subshell, and 8f7 by 2 for a half-filled f subshell. Vector model for 2 valence electrons under LS coupling scheme. This is a common type of coupling which occurs in most of the lighter atoms. In the vector model for LS coupling, the individual orbital angular momentum vectors L1 and L2 of the 2 electrons are strongly coupled to each other to form a resultant orbital angular momentum vector L, about which both L1 and L2 precess rapidly. The corresponding quantum number L can take the values. L is equal to L1 minus L2, L1 minus L2 plus 1, L1 plus L2. This gives the various terms of the atom, and these terms are designated as SPD terms corresponding to L is equal to 0, 1, 2. Similarly, The individual spin angular momentum vectors S1, S2 of the two electrons are strongly coupled to each other to form a resultant angular momentum vector S, about which both S1 and S2 precess rapidly. The quantum number S can take the values S is equal to S1 minus S2, S1 minus S2 plus 1, S1 plus S2. And since S1 and S2 are equal to 1 by 2 and we have S is equal to 0, 1. Thus, multiplicity 2s plus 1 has values 1 and 3, that is, the two valence electrons lead to singlet and triplet terms. As a result of spin orbit interaction, L and S are rather less strongly coupled with each other to form a total angular momentum vector J of the atom, that is, J is equal to L plus S. Both L and S precess slowly around J. The quantum number J can take the values J is equal to L minus S plus 1, L plus S. Thus, the spin orbit interaction breaks each level characterized by an L value in a number of fine structure levels, each characterized by a small j value. The collection of fine structure levels is known as multiplet. So, the figure depicts the LS coupling, where we have already described that these capital L and S, the resultant of them gives the J. There are selection rules for the interaction of LS coupling. In the electric dipole transitions in multi-electron atoms, the selection rules are: for one valence electron system, delta L is equal to plus minus 1, delta S is equal to 0, and delta J is equal to 0 plus minus 1, but J is equal to 0. For multi-valence electron system, delta L is equal to 0 and plus minus 1, and delta S is equal to 0. Delta J is equal to 0 plus minus 1, but J is equal to 0. There is no restriction on the total quantum number n of either electron. Only transition between even and odd terms are allowed for dipole transition. Now, JJ coupling. The JJ coupling is an opposite extreme to the ideal LS coupling and is approached by heavier atoms, for which the spin orbit magnetic interaction terms in the Hamiltonian predominates over the residual electrostatic interaction and the spin-spin correlation. This means that the interaction between the orbital and the spin momenta of a single electron is much greater than the interaction between the spin momenta of different electrons. Therefore, in this case, the splitting of unperturbed energy level due to the introduction of the various perturbation takes place in the order spin orbit interaction, residual electrostatic interaction, and spin-spin correlation. Due to strong spin orbit interaction, the orbital and spin angular momentum vectors of each individual electrons are strongly coupled together to form a resultant angular momentum vector J of magnitude h cross j into j plus 1 under the root, where j is equal to L minus 1 by 2 and L plus 1 by 2, that is, j takes half integral values only. This means that due to spin orbit interaction, the unperturbed energy level is separated into a number of well spaced levels, each corresponding to a different combination of the possible j values for the individual optical electrons. The level corresponding to all the electrons having their smaller j value, j is equal to L minus 1 by 2, being lowest. As a result of the residual electrostatic interaction and spin-spin correlation, the resultant angular momentum vectors J of the individual electrons are less strongly coupled with one another to form the total angular momentum vector J vector of the atom of magnitude J into J plus 1 under the root h cross. The total angular momentum quantum number takes the values J is equal to J1 plus J2 plus and so on minimum to J1 plus J2 and so on minimum plus 1 and J1 plus J2 and so on. This means that each of the above level is further separated into a number of levels characterized by different values of J. And to understand this coupling, let us take some examples. For p electron, L1 is equal to 1, S1 is equal to 1 by 2, and so J1 is equal to 1 by 2, 3 by 2. For the d electron, L2 is equal to 2, S2 is equal to 1 by 2, and so J2 is equal to 3 by 2, 5 by 2. This gives 4 J1 J2 combinations of possible J1 and J2 values. These are 1 by 2 3 by 2, 1 by 2 5 by 2, 3 by 2 3 by 2, 3 by 2 5 by 2. Thus, a spin orbit interaction splits the unperturbed energy levels into 4 levels, of which 1 by 2 3 by 2 lies lowest and 3 by 2 5 by 2 lies at the highest. Each of the above 4 levels is further separated by residual electrostatic interaction and spin-spin correlation into a number of J levels equal to the number of integrally spaced values of J that can be formed out of the 2 J values. The above 4 J1 J2 combination gives J values as has been depicted in the figure. 1 by 2 3 by 2 pair gives J is equal to 1 2, and 1 by 2 5 by 2 gives J is equal to 2 3, 3 by 2 3 by 2 gives J is equal to 0 1 2 3, and 3 by 2 5 by 2 gives J is equal to 1 2 3 4. So the complete splitting of the 4p 4d level comes in a way that the different pairs of J values gives us fine levels of the structure. Spin-spin coupling. Spin-spin coupling is the coupling of the intrinsic angular momentum, means spin, of different particles. Such coupling between pairs of nuclear spins is an important feature of nuclear magnetic resonance (NMR) spectroscopy, as it can provide detailed information about the structure and conformation of molecules. Spin-spin coupling between nuclear spin and electronic spin is responsible for hyperfine structure in atomic spectra. Term symbols are used to represent the states and spectral transitions of atoms. They are found from coupling of angular momenta mentioned above. When the state of an atom has been specified with a term symbol, the allowed transitions can be found through selection rules by considering which transitions would conserve angular momentum. A photon has spin 1, and when there is a transition with emission or absorption of a photon, the atom will need to change state to conserve angular momentum. The term symbol selection rules are delta S is equal to 0, delta L is equal to 0 and plus minus 1, delta L is equal to plus minus 1, delta J is equal to 0 and plus minus 1. The term symbol selection rules are delta S is equal to 0, delta L is equal to 0 plus minus 1, delta L is equal to plus minus 1 and delta J is equal to 0 plus minus 1. The expression term symbol is derived from the term series associated with the Rydberg states of an atom and their energy levels. In the Rydberg formula, the frequency or wave number of the light emitted by a hydrogen-like atom is proportional to the difference between the two terms of a transition. The series known to early spectroscopy were designated sharp, principal, diffuse and fundamental, and consequently the letters S, P, D and F were used to represent the orbital angular momentum states of an atom. In atomic nuclei, the spin-orbit interaction is much stronger than for atomic electrons and is incorporated directly into the nuclear shell model. In addition, unlike atomic electron term symbols, the lowest energy state is not L minus S but rather L plus S. All nuclear levels whose L value orbital angular momentum is greater than 0 are thus split in the shell model to create states designated by L plus S and L minus S. Due to the nature of the shell model, which assumes an average potential rather than a central Coulombic potential, the nucleons that go into the L plus S and L minus S nuclear states are considered degenerate within each orbital. For example, 2p3 by 2 contains 4 nucleons, all of the same energy. Higher in energy is the 2p1 by 2, which contains 2 equal energy nucleons. Now, there are selection rules in JJ coupling. The parity of the configuration must change in an electric dipole transition which is Laporte rule. This means that if only one electron can jump in the transition, then for this electron we must have delta L is equal to plus minus 1. If two electrons jump, then delta L1 is equal to plus minus 1 and delta L2 is equal to 0 and plus minus 2, and delta J is equal to 0 plus minus 1 for the jumping electron and delta J is equal to 0 for all the other electrons. For the atom as a whole, delta J is equal to 0 plus minus 1, but J is equal to 0. Now again there is a vector model for the electron atom under JJ coupling scheme. In the vector model of two electron atom number JJ coupling scheme, the orbital and the spin vectors L1 and S1 of one electron are strongly coupled to each other to form a resultant J1 about which L1 and S1 precess rapidly. The figure depicts the same. Similarly, L2 and S2 of the other electron form J2. Now the vectors J1 and J2 are less strongly coupled to each other. The figure clearly mentions that they are quite less strongly coupled and form the total angular momentum equal to J of the atom. The vectors J1 and J2 precess rather slowly about J, again shown in the figure. So, in conclusion, what we have learned is that atoms with two or more equivalent electrons has same n and l values. The values of at least one of the remaining quantum numbers ml or ms must differ in order to satisfy the Pauli exclusion principle. And we have also understood Hund's rule that explains the relative energy of the various levels. Vector model for two valence electrons under LS and JJ coupling schemes, selection rules under LS and JJ coupling schemes, and the term of non-equivalent electron and that are of equivalent electron has also been discussed under LS and JJ coupling schemes. Thank you.